Hi, my name is Simon Eschbach and I'm from Sledgehammer Games in Melbourne. Today I'm going to be talking to you about optimizing the UI's CPU-bound frame rate in Call of Duty. This talk is also informally known as Operation UI Code. Let's get started.
Hello?
Hey, it's Dan. We've got a problem.
What is it?
It's the UI. It's infiltrated our borders.
Alright. I can help. But I'm gonna need a team.
Assemble it.
That took a lot longer than I care to admit in PowerPoint. So this image depicts a ghost aiming down the sight of a sniper rifle. This image also depicts what I imagine rendering and engine programmers look like when they start sifting through the user interface code of a game engine. I've made an entire career out of taking that look under the covers of user interface systems, and I have to admit I have seen some things. Today I'm going to tell you a story of how we had one of those classic game development moments when you're working really hard to get a game ready to ship, and you get a message, in this case from Ghost himself, informing you that the game performance has atrophied to a point where the frame rate was no longer hitting its vital 60 FPS target, and that the UI had a large part to play in that problem. The mandate was simple: assemble a team and fix it quickly. And so it was done. The UI Spec Ops Ensemble, also known as Task Force 141, was a specialist team armed with various profilers to obliterate poor CPU performance and take no hostages. The team was assembled specifically for one purpose: Operation UI Code, and it consisted of Alistair Hatt, Stephen White, Jared Dowsey, myself, and Dan Nelson, also known as Ghost. Part 1: The State of Affairs. The engineering of user interface systems is often one of the most overlooked parts of a game engine. What's worse is that these systems can be deceiving. Time and time again, I've seen UI systems written with the best of intentions to empower design with powerful and flexible editors, often including a scripting language that allows menus and gameplay to be quickly brought to life. The thing is, it works, at least for the first release, and herein lies the deceiving nature of it all. Over time, complexity increases. Features need to be quickly developed and iterated over. Widgets start to get copied and pasted both alongside and inside of each other. The UI scene hierarchy gets wider, deeper, and more complicated, and the scripts bloat and spaghettify. Before you know, the system that used to empower designers with the ability to modify the UI with high quality and at high velocity becomes slow, bloated, and brittle. And performance-wise, well, that's what this talk is about. This talk details my experiences shipping various Call of Duty titles. As can often happen during the development of the games that we make, the rush to reach feature completion can take precedence over optimization until the very tail end of development. This is the story of the day that I was called by Ghost. He was right. We did have a problem. The UI was taking over half of our 16 millisecond budget on Gen 8 platforms. We were heavily CPU bound, and this was impacting our ability to keep the game running at 60 FPS. Hoping that I perhaps took a bad profile, I took a look at the profile histogram to make sure this wasn't just an intermittent frame spike due to some kind of processing, but as you can see, this wasn't the case. The UI was consistently taking this long to process. This capture wasn't even a particularly complex use case. It was nothing more than a local capture with a few bots. Original profiles showed our more complex game modes chewing as much as 12 milliseconds in playtests. This obviously was not good. So 8 milliseconds. How could we spend so much time rendering quads? Here is a typical Call of Duty gameplay HUD. And this is what the UI's CPU frame step looks like on Call of Duty to get those quads ready to render. It starts by ticking its tweens. It then binds data from the game. After this, the Lua runs callbacks on any modified data that requires pre-processing before display. Input and other events are then processed. We then perform the layout step where layout logic is applied. The draw list is then built based on the results of this layout step, so this is where the quads are generated. In this capture we have some thread contention, which we can ignore. And after that, the quads are finally sent to the GPU for render. The thread contention was fixed, so just ignore that. Now, a few things to note regarding an optimization strategy for all of this. Our UI frame step is monolithic and it runs on the main thread. As such, it is a prime contender to block the critical path to render. The dependency chain of our process leads to limited options for parallelization. As our UI is highly dependent on displaying up-to-date data from virtually all other game systems, it needs to run at the end of the frame step. So moving this monolith onto a worker thread, it gains no real benefit as it simply creates main thread contention as the main thread sits and waits for the UI processing on the worker to finish. And then running one frame behind, so we could process the UI in parallel at the start of the next frame to avoid such contention, simply isn't an option. This is Call of Duty. Our players can tell if we show the enemy nameplates one frame late. If we delayed the entire UI a frame or desynced the HUD elements by a frame from world space, I can say with a high degree of certainty that all hell would break loose. This was just a long way of me saying we investigated our options. There was nothing we could do, and nothing we could change outside of the process itself to stop this from blocking the critical path to render. I always like to boil the UI down to this. How many quads is the UI rendering to the screen in any given frame, and how many of those quads actually change state in the last frame? Thinking about it this way, the HUD should theoretically be computed in nothing more than, say, a millisecond, provided we pushed our data efficiently. Unfortunately, years of scripting has paved the way to high levels of complexity. It's important to remember that this game has 20 years of iterations under tight deadlines and has bounced between a lot of studios and even more engineers in that time. This is what has paved the way for the complexity we need to detangle today. So far I've spoken of the sustained frame time, but now I want to take a moment to talk about spike frames. Spike frames in the context of this presentation are defined as being long enough in duration to cause the game to visibly stutter or drop frames. In this example, as we are taking far longer than our 16 millisecond target to render a frame, we end up showing the same frame about 5 times in a row as we wait for the CPU to finish its work. 5 times in a row just based on 60 FPS with VSync. So this is not ideal. While performing further reconnaissance, I found significant frame instability by spikes being caused by all kinds of different things for all kinds of different reasons. Here is an example with a 90 millisecond spike occurring multiple frames in a row. The player experience of this example is a persistent stuttering feeling when frames are dropped multiple times in succession. So freezing, stuttering, chugging, doesn't really matter what you call it. In an FPS, the player experience is severely compromised by dropped frames. They make us sad. Well, I know they make me sad. When I play a game, I expect it to be perfectly smooth at 60 FPS at a minimum. I don't want to see a single stutter or a single dropped frame. Even when I'm using a smartphone, I notice every little bit of lag. The iPhone keyboard lags sometimes. I want to profile it so badly. But this is more important than texting my mum. This is Call of Duty. And in this game, drop frames can be the difference between getting a kill or being one. For the purposes of Operation UI code, I defined stutters one step further. Stall frames. Stalls are perceived as more than a stutter. They're a flat-out freeze in the gameplay. In our UI system, these were often caused by Lua performing emergency garbage collection because the VM was running out of memory. When we had these emergency garbage collection cycles in succession, we experienced stalls in the realm of 500 milliseconds up to an entire second. Such a problem was exhibiting itself frequently during gameplay, and destroying the player experience. Here is one such example. This is not a streaming error, albeit this was a worst case example. This is what we were dealing with on the PS4 right up until the wire. This example will stand out in my mind for a long time for reasons I will explain later in this presentation. Once performance has degraded to this point, the game is virtually unplayable. So hard stalls. These are what can really make players rage. They might get you killed right towards the pointy end of a game, and they're dangerous for both you, your kill-death ratio, and they're dangerous for televisions as well. Part 2. The offensive. The enemy infiltration was strategic. We were attacked at a very inopportune time, right when our defenses were weakest, right before we shipped. This is why the 141 was called in. I'm going to be honest with you, in the context of where our UI system had gotten, trying to fix the frame rate in time for launch was an absolute scramble. But there were some mechanisms that we could employ in the short term to at least organize ourselves and classify the problems. We also had 4 of us, so we could afford to split our efforts into different locations. Let's define some basics based on where the initial numbers were at. Sustained frames were considered anything under 10 milliseconds. Spike frames were considered from 10 to 100 milliseconds in duration. Stall frames were anything longer than 100 milliseconds. Separating our frames into these categories helped us to classify the likelihood of where problems lay, by which extension allowed us to group and triage the types of problems between us. When it came to the sustained frame time, this was where Stephen and I lived. Sustained frame time tends to be addressed through systemic fixes, as it's the system that is either being inefficient or simply malfunctioning on a persistent basis. When it came to spike frames, this is where Alistair and Jared mostly worked. Spikes tend to be best addressed in a longest spike first triage process, which then leads the way to understanding different classes of spikes within each subsystem. Stall frames, like the one in the video I just showed you, were solved by a team effort I'll explain later in this presentation. We had to get to work fast. Given the stakes, all optimization types were on the table. This was a matter of fix it, ship it. After having spent many years optimizing the CPU, I found certain classes of optimizations to be useful in particular situations. While these classifications are not hard and fast rules, and each optimization type helps both sides of the fence, they did help us to work down the CPU cost pretty quickly. Sustained frame time tends to be improved with analysis of the core C++ systems. This means investigating the validity of element invalidations, ensuring our caching mechanisms are working properly, and doing what can be done to avoid costly element tree traversal. By the way, when I say cache, I mean cache. This is just how we butcher words in Australia. Optimizing hot code paths are a contender for sustained frame time improvements for obvious reasons. There's big bang for buck there. While I'd never personally recommend using a memory managed language for a real-time application, here we are. And in our case, tuning the garbage collector to step consistently and reliably was an important consideration. Lazy initialization can often be used to avoid processing of objects or data which are not used. Alistair found that about 50% of data bindings, for example, were unused due to the amount of data that was game mode specific at runtime. Staggered processing of some systems over multiple frames was also employed to get the game out the door, although I don't recommend this approach for the long term, and while using it is normally indicative of a large architectural problem, it can cut processing into half or a third, depending on how many frames you space it out over. But I will say it does tend to cause edge cases and artifacts down the line, but hey, in a pinch, you got to do what you got to do. Now, when it comes to the frame spikes, algorithm complexity reduction is the first port of call. Unscalable algorithms love to spike frames, and as data grows, it obviously gets disproportionately worse depending on the order of complexity being dealt with. Caching data can be an effective access pattern for costly calculations, but this is a double-edged sword as it trades memory for CPU performance. Over time, the caches grow to problematic sizes, which we are feeling now, but you've got to give them credit, they helped us out in a pinch. We created a way to avoid large event broadcasting spikes with a system that provided a direct mechanism for event communication by dispatching the events directly to the subscribers. We also avoided font cache misses by writing diagnostic tools to better prime the font cache so that we wouldn't hitch when needing a glyph and needing to render that into the render target. And finally, hand optimization of scripts is just the time-consuming and difficult task, or the laborious task of addressing spikes in script on a case-by-case basis, looking at what the code's doing, figuring out how to do it faster, or just cutting things out of it that are not necessary. Of course, there's many other ways to optimize code, but these were the main weapons in our arsenal on this project and in this short timeline. To illustrate an example of sustained frame optimization using UI system analysis, we turned our heads to this costly little squad status element that kept chewing huge CPU time even when nothing was updating. As you can see, it was chewing a whopping 766 microseconds sitting in the corner of the screen doing seemingly nothing. The histogram showed that this element was a sustained frame problem and not a spike. Through some deeper digging, we discovered that it was continuously redrawing itself due to a bit flag that was enabled, which was called run layout every frame. This sounded suspect to say the least. After digging through the C++ and Perforce history, it became apparent to us that this flag was added so that widgets could treat the layout function as a sort of element tick to run logic. This was not a good idea, as by tying a widget's logic tick to its layout process, the element needs to constantly run its layout code to ensure the update code runs, and then it invalidates its quad caches and redraws itself every frame. So elements with this flag enabled would redraw themselves every frame, even when nothing was changing or even if the element was invisible. This flag was a hack to begin with, but it caused another problem by extension. Since the UI is hierarchical by nature, if a child element invalidates, it causes all of its parents to invalidate too. Tracing these issues backwards, run layout every frame was introduced many years ago as a solution for updating countdown timer text in C++. In this case, the entire squad element was constantly redrawing itself because it had squad revive timers ticking away, even when no squad member was down. Over the years, this flag was then copied and pasted 40 times. These elements were then proliferated using the design tool, and after a number of years, half of the UI was redrawing itself every frame with no caching, including the grid, which meant that the entire frontend would constantly invalidate. There was no time to fix this properly for launch, so we clawed some time back by removing the revive timers from the element hierarchy when they were not visible. This alone saved several hundred microseconds, but didn't fix the root of the problem. But from these learnings, we added this to the following year's roadmap. Stephen worked tirelessly to make an impressive change when he corrected this and separated the layout logic from the tick logic. The result was a 40% reduction in gameplay layout and draw list duration and a greater than 20x improvement on the front end, since virtually everything existed inside of a grid. This process of discovery, followed by a ship hack fix, followed by a roadmap to a proper solution, became a standard workflow for my team. I mean Task Force 141. To illustrate an example of stall frame optimization using algorithm complexity analysis, I can point to the simple and classic ON squared example. While there were many more interesting examples of complexity reduction, this one's a good one to demonstrate my point. Have a think about how long you think a stall that continuously trips the garbage collector could possibly take. I'm going to present 3 options for you to think about. 200 milliseconds, maybe 500 milliseconds. What about an entire second? I'm just trying to keep you on your toes. The answer was none of those. It was actually 20 seconds long. The game would literally freeze for 20 seconds and then come back to life. Now, you would invariably come back to life too, because there was a 99% chance that you were killed by an enemy while that happened. While a lot of this stall was incessant looping, the real issue was that the memory would continuously run out during this process, and the garbage collector could not keep up with the allocations, thus leading the way to lengthy garbage collection cycles so the game would essentially stall indefinitely. While I've since stopped the garbage collector from having the capability to take control of the machine like this, it was pretty disruptive to the player experience, to say the least. So essentially what's happening here is that we're looping through all of the stickers. Stickers are, MTX that you can attach to your weapon. And then we were going 2 functions deep, and then looping through all of the stickers again. Of course, with an ON squared algorithm, it doesn't take much data for things to get out of control. So how many stickers do there need to be for 2 million iterations at ON squared? And square root of 2 mil, 1,414 stickers. That's really not that many, and as the live season progresses, more stickers are added. So once we get up to 2,000 stickers, we end up at 4 mil iterations, or 28-second stall. 3,000 stickers, 9 million iterations, and you're stalling at over an entire minute. But getting back to the code at hand, while it's easy to visually pick out a nested for loop in the same function, when loops cross file boundaries like this, algorithm complexity can be harder to statically identify and even more difficult to pick up in code reviews. In this case, we had a nested loop achieving ON squared complexity across files, while making proper use of hash maps inside of the inner loop took us from n squared to n and corrected other calling code from falling victim to this inefficiency. ON is still not good enough if you really want to scale. Irrespective of patching this particular example, everything I'm saying right now is just a temporary fix. Going through spaghetti to reduce algorithm complexity is futile. You need to stop writing the spaghetti in the first place. In addition to this, we shouldn't be iterating entire lists of content at runtime in the first place. For example, data should be pre-computed where possible, paged where possible. Otherwise, access patterns should be logarithmic where possible. So the 2 main issues I take with the prior examples are the following: the garbage collection being used in a real-time application, and the runtime data processing, and a distinct lack of language features or API for efficiently querying said data. So let me start with the data. Lua and for loops, and then for loops in for loops, and then loops in loops with if statements in them. No. If this is what needs to happen in order for programmers and designers to get their work done, then we have failed to provide a suitable platform for the development of a real-time application. We've failed to provide our engineers with the tools necessary to do their job. They're doing earthworks with a shovel, and they're working so hard to get their jobs done, but what they need is an excavator. We identified that a lot of our stalls were coming from excessive iteration, which was in turn causing the garbage collector to run wild. There is only so much garbage collection tuning that you can do in this sort of situation. To get away from these loops, we needed to go back to the build pipeline and arrange our data in a format that would allow us to operate on it quickly. One simple example was adding an ordered index to our data so we could perform binary searches on lists at runtime. We then created a query system inside of the runtime that would allow us to query the data from Lua in native code. So we went from this code iterating ON through our operator table to determine an operator's index based on its reference, to this, the ability to query for this sort of information in a single line of Lua. And this ultimately calls into C++ to perform a binary search on the data, which was sequentially ordered in that build process. As a result of such a change, we've achieved a few things. 1. The user code is simplified and less bug-prone, less boilerplate code. 2. The code now executes in C++, so it no longer needs to stress the garbage collector. And 3. The code has gone from ON to O log n using a binary search. While this example is simple, this can be built upon. The query system can be extended to perform joins, filtration, and ordering, all within a generic C++ implementation that keeps programmers making great user experiences and not debugging what becomes hard to follow and error-prone code. So big thanks to Jeff Colhan for his work on this. Just want to shout that out. Now moving on to the garbage collection, which I also take issue with. First, if you're thinking of introducing a garbage collector to your game, I would advise against it. If you never do it, you will not have to deal with the problems that arise. So my first piece of advice is just don't. If you do a bit of Googling for garbage collection best practices, it's astounding the number of gotchas and caveats there are to just waiting to catch you out. String concats, copying arrays, closures, anonymous methods, boxing, moving variables, outside of loops to stop locals from being created. Good luck keeping on top of this with a large development team. There is only so much information a programmer can retain at once. Is it not better for engineers to focus on the problem at hand versus following hundreds of arbitrary rules in a coding standard that are simply in place just to avoid the unsuitability of the system underpinning it, and then spend the better part of a day getting a review over the line? No. So that was a bit of a rant, but let's just assume we're using our garbage collector, and you notice this sort of thing happening. The garbage collector is humming along, but unable to keep up with memory consumption, so it intermittently spikes to clear a bunch of memory out. What are our options here other than making sure nothing is silly going on with the allocations, of course? Implementation-wise, I'll be speaking of LuaJIT and a two-level segregate fit allocator. Now, let me first pay credit where credit is due. LuaJIT paired with the TLSF allocator are impressively fast and work very well together. The problem does not lie in the underlying technology. The problem lies in how we're using it and the use case that we are applying it to. When it comes to garbage collector tuning, there's a few options. So one option is a partial step that runs until it frees up to a certain kilobyte threshold. The other step is to go, the other option is to go nuclear and just perform a full collection, which you see garbage collectors do when they reach their emergency thresholds. The problem with both options is that you end up relinquishing control of your CPU to the GC algorithm until it's finished its mandate of clearing a certain amount of memory. This makes me very nervous. How could you give up control of the precious CPU to an algorithm that will take an indeterminate amount of time to run in the context of a game engine? This is just not a good idea. As you can see from my frustrated squiggles using my beloved snipping tool, trying to tune the GC using a memory threshold alone was unable to cope with the dynamic allocation patterns demanded by the UI, and when it needed to, it took its sweet time to iterate the pool and free the necessary blocks up to our predetermined step threshold. But what if we did this? We tell the GC to do the smallest, most atomic step it can possibly do. This way we can control it better and don't need to relinquish control to the collection algorithm as much. So doesn't this sort of code instantly lower your sort of anxiety regarding this? It certainly does for me, because we're taking control of the CPU back here. With this strategy, we're now in charge of the amount of the time that the GC takes. We define how much time we want to allocate to it. So in this case, 100 microseconds. We get it to perform its minimally indivisible step with a kilobyte threshold of 0. And we will just run that until the timer runs out. There's also a return type on this, so if there's nothing to free, then you can bail early, but I've just simplified the code for the sakes of this talk. So this strategy can also be modified. In this case, we've statically defined 100 microseconds, but based on your allocation patterns, this GC time slot could be rubber banded and allotted more time when the garbage collector is under stress. But anyway, in our case, this was adequate, and after limiting the garbage collector and using a minimally indivisible step, we ended up with some pretty nice results, with the GC humming along at between 130 to 180 microseconds per frame, spiking in the worst case to around 240 microseconds. As we process this garbage collection cycle on a worker thread outside of the Louis step, closer to the beginning of the frame, this work is actually achieved in parallel and for no real cost to the frame rate. Obviously, this needs to run when the global interpreter lock is not in place, so it actually parallelizes quite well. But just remember what I said. It's easier to not go down this path because all it takes is some inefficient code to undo all of this work. Part 3, the clutch. While we were well on our way to optimizing our way out of this mess, we still had one blocking issue that was destroying us, and we couldn't work out what was going on or how to fix it. So we were 4 days from launch. We release in 4 days, and we're out of time, Simon and Dan. The PS4, it's chugging like mad. Do you mean non-stop in the literal sense, or do you mean it's one of the most common ones observed? Yes, literal. What build is this? All PS4 package builds. It looks like any fix will need to be in C++ and require a new executable, so we can't patch.
We'll push an ETU. Get the 141 on it.
Well, you heard Ghost. We'll perform an emergency update, so let's get it done. This was the video I showed you at the start of the presentation. This was the classic Swiss cheese effect. As we were frantically trying to fix the frame stalls, we found a ticket that had been marked into the wrong bucket. Looking through the ticket history, this problem had existed for some time, although we never saw it in our local captures because it was package only, release branch only. This was happening with 100% reproduction for QA and playtests, but not for us running our local builds. I spent a sleepless week trying to reproduce this and fix it blind, but to no avail. We had 4 days left until launch. I called the 141 into a Zoom. I was desperate, and I couldn't do it alone. We immediately launched into a full-blown assault on the issue. This was one of the most remarkable team efforts that I've ever had the privilege of being a part of in my career. With 4 days until ship, Stephen hammered away trying to get a local repro and managed to get the hitching started by hopping into a vehicle and refueling it. I still to this day have no idea how this got us local reproduction, but I'll take it as a gift from the gods. Alistair got the release branch and sideloaded a special diagnostic profile build against the package that would give us the ability to further diagnose the problem. He then followed Stephen's vehicle refueling repro steps and took the capture. We analyzed the capture and found that the offender was some high order of complexity code in the objective system sending the Lua VM out of memory. It wasn't immediately clear that this was the cause as we were running out of memory in the next frame oftentimes, but it showed us where to look and turned out that the incremental GC just couldn't keep up. It turns out this was only reproducible in the big map and never happened in a local test because there wasn't enough players and objectives active when playing with only bots or in a few dev kits. With a few insights about the objectives code, Jared created a C++ fix to eliminate the complexity from the objectives algorithm. In a nutshell, loads of data was being sent to Lua for processing, as each objective contained 32 slots for locations, and rarely used all of them. In addition to this, we could also prune objectives that were empty as well as objectives that were active, as they didn't need to be displayed in world space. Alistair then verified that it worked against the package, and took profiles to verify the fix's efficacy. We then put the code up for review and kicked off the ETU build to fix it 72 hours before launch. That was close. So, as you can probably guess, we did it. Call of Duty, as it always is, was released on time. Many battles like this are fought across all departments to get our game out the door each year, and I have huge respect for all of the Activision studios that help to make our game a reality and such a commercial success. Now that we had put the work in to get the game out the door, without a solid plan, performance atrophy would creep back in and this sort of ship risk would just be a repeating occurrence. This was a battle we were only going to fight once. Part 4, Battle Hardening. This close call exposed a huge vulnerability in the code base, but it also forced us to do a deep dive into it. The goalposts had moved, and this time to a more ambitious place. The aim of the game was now to further improve the frame rate to get the worst case and slowest platform frame time down to under 4 milliseconds, improve processes pertaining to CPU performance, improve diagnostics, and automate performance testing. Now, when I talk about 4 milliseconds, keep in mind that this is PlayStation 4. Newer platforms can actually run this code much, much faster, but 4 milliseconds or less on the PS4 based platform was quite ambitious, considering that we were sitting at over 7 milliseconds at the time, and the PlayStation 4 CPU was released over 11 years ago now, and it clocks in at a meager 1.6 gigahertz. And to put this into perspective, obviously the smartphone in your pocket has a significantly more powerful CPU, but this was even considered an underpowered CPU in 2013 when the console itself was released. So this is where we're seeing very slow frame times. But regardless of the challenges, I delivered a roadmap to outline the way in which we would work towards our target. The thing is, you can't fix what you don't have a metric for. In this last battle for 60 FPS, I had loosely defined different types of hitches based on their duration, and then tried to triage and work backwards from there. The aim of the game was get it shippable, which generally meant getting the frame time down to something that didn't impact the baseline FPS too much and didn't have obvious stalls. Most of the work we carried out was stall related. While we made about 1.5 milliseconds worth of progress on the sustained frame time, it wasn't enough to fully unblock the main thread. One of the problems with our measurement technique was that we were taking the mean frame time from short profiles that we took on our own dev kits with bots. These types of profiles are too granular and polluted to give an indication of an overall performance trajectory. Capturing actual playtest metrics is key. But before even considering where performance should be measured, it's important to set up guidelines for how performance will be measured. Taking the statistical mean of a playtest capture is not a useful metric for generalized CPU performance. The reason for this is because the statistical mean in such a long capture will collapse the concepts of sustained frames and spike frames into a single metric. It's important to measure both of these metrics separately to ensure we eliminate the noise of frame spikes from the sustained frame time measurement. This is why medians are used for performance tracking. The 50% median provides an excellent metric for sustained frame performance, while the 99th percentile median will give the 1% worst performing frame spikes, and then we can go a step further to the 99.9th percentile median, which will give an accurate representation of the duration experienced by the worst 0.1% performing frame offenders, or the frame types I previously referred to as stalls. Using a metric-based methodology like this not only defines a much better way to categorize and triage stall types, it also provides accurate metrics for long-term tracking of performance data. Which brings me to my next point. Measurement is of no use without accurate and consistent sampling. A game-changing development in our current process is the CPU performance dashboard that was set up by Liam Gilbride. The dashboard took existing FPS tool measurements from playtest builds and sent them to an elastic dashboard for analysis. This allowed us to track CPU performance for each part of the frame step for each level over time. This was ultimately how we defined progress and success criteria for CPU performance well beyond the scope of just the UI. But using it specifically for the UI was a godsend, and we could view our progress over time visually and with great accuracy. On the left you can see stall frames in red, spike frames in blue, and sustained frames in green. On the right you can see a histogram of frame time distribution. This is filtered to a 4-month period, although the dashboard can be customized to any chart, query, or time span to create anything or any visualization desired. But a dashboard's efficacy is only as reliable as the data you send it, and this is why establishing a reliable process for capturing this data is so important. Establishing processes for QA to perform 2 playtests a week in the profile build configuration, tested across a variety of game modes and levels, ensured that we had a steady stream of data flowing into the dashboard that reflected a real player experience. In addition to this, we educated QA on how to take razor captures for closer engineering analysis. It was in this channel that we could also make QA requests for captures of spikes we needed more information on. So by now we have established how we measure the data, where we will measure the data, and where the data will come from. While this is all good and well, the data is useless unless we have the diagnostic tools and means to act on it. It is for this reason that profile marker verbosity was moved to a toggleable switch in the profile build. This meant that QA could flick various levels of user marker details on and off based on our investigative requirements. For example, I needed the highest level of granularity. I would ask for a short capture of the highest possible detail during gameplay to investigate the state of quad caching as we color-coded user markers to get a glimpse into which of our quads were invalidating and if the invalidations were necessary. Or I could use this mode to quickly run a local test to see what assets were being looked up on a lengthy menu transition or stall within the game. Having the profiler in this manner, using the profiler in this manner and being able to change the level of detail of our profile markers on the fly made diagnosing problems much faster, and having established processes and support from QA meant that engineers didn't need to spend their days working for reproduction. We could simply ask QA to flick on a switch and to take a capture of their reproduction for us. In the same way you might ask for a video of the problem, we would simply ask for a verbose profile capture. This would often point us to exactly where the problem was originating from. So obviously, just one thing that I will add is that you don't want to have a high level of profile verbosity in your markers turned on at all times, because this really pollutes the captures and also overflows the user marker buffers, which are obviously not infinite. So generally speaking, it's best to balance your normal profiling mode to have a number of markers that can point you to which, say, department or domain a problem may be in, but then have more detail available if you need to run a little bit deeper of a diagnostic analysis. So while it's all good and well to establish these processes to be able to deliver a stable product, we're now taking it a step further. So no more surprises. The roadmap for 2024 is to get our performance tests running on continuous integration per commit, with thresholds set on automated performance tests which break and turn red when exceeded. This allows us to immediately detect when slow code was added and roll back the change, and it also allows us to keep tabs on seasonal memory consumption and general performance atrophy. This has the added benefit of being a learning opportunity for the engineer responsible for the change, with the idea being that engineers can be coached on topics regarding to performance, algorithms, data structures, and other engineering first principles. Automated test performance metrics are already functional, where we track the internals of the UI system on each commit. In the above example, you can see the incidence of spike frames decreasing over time as we optimize them out. Here is another example of where a change has introduced a frame stall. While this is still a work in progress and we need to further build out our tests and stabilize the data, even in its current state, it's been really effective in catching performance and memory regressions. Now, regarding our frame targets, did all of the stuff I just spoke about end up working, and did we hit our 4 millisecond goal on the PS4? keeping in mind that we were coming down from 12 milliseconds. We did achieve it, and we managed to get the sustained frame time down to 1.2 milliseconds for the single player, 2.1 milliseconds for multiplayer, 3.1 milliseconds for ground war, and we literally just squeaked the Warzone target by 100 microseconds at 3.9 milliseconds. So I would like to thank you all for listening to my presentation today. There were many talented individuals that were a part of this battle, and if there's one thing that I'm truly proud of, it's the way in which we all work together across time zones, countries, language barriers, cultures, and studios to pull this game together. So with that, I will wrap it up. Thank you very much for coming to listen to my presentation.
Thank you very much, Simon. I'll wait for him to join the webinar live so we can do Q&A. And kudos for Simon for wearing the same t-shirt. This continuity game is really dead on. So, I've grouped these up in a couple of different functional areas, Simon. So I'm going to start with team and timeline questions, which I think some of which you did address very early on, but I think people forgot. And so from Arash, he asks, what was the time frame again for this effort? And then Tom Everett asks, other than the 5 folks, that you mentioned, how many other sort of external operatives were there, whether that's UI and UX teams themselves, and their involvement of it. So maybe you can speak to that briefly.
Yeah. So the time was about 6 weeks from the call from Ghost to actually launching. So it was pretty tight. Yeah. And then as far as external operators, I think that the issue was that everyone was just trying to get the game finished, and this was kind of recognized, at the last moment. And so we were just brought in to focus purely on performance so that everybody else could just finish making the game. So it was really just us doing that perf work at that time.
Right. And then Balder kind of, adds in a question around, timeline and prioritization, which is, did you make any decisions between prioritizing stalls and sustained time if you weren't sure you're going to get everything done, by the end? Like, how are you trying to triage those relatively?
Yeah. So I guess initially I just went deep into the C++ and realized, like, what can we do for a sustained, angle. But really it was the stalls that was going to sort of block submission and really, impact the viability of launch. So we definitely needed to focus on the biggest stalls first in that regard. But at the same time, the baseline FPS needed to be brought up as well in order to hit our sort of Call of Duty standards. So they were both very important, and that's why we split a little bit with Stephen and I working on the sustained time, and then Jared and Alistair working on those big spikes. And then at the very end for the stall, we all just smashed together and figured it out.
It's like Voltron, yeah.
Yeah.
Another theme that came up was around QA and process. So Melek Bengugam asks, what is your routine when profiling and evaluating performances? Are you helped by QA? I think you touched on this a little later on in terms of requesting specific captures. And then Cream Lucian asks, do you have a way to dump a frame for playback as a way to repro those only on my machine type of perf bugs in UI? I know you kind of talked a little bit about being able to tick on certain user markers and things like that, but maybe you can kind of address the QA side and
Yeah. So like we've certainly improved our sort of education for QA as far as profiling is concerned, each release since then. And essentially, we need really good processes for like profile test captures, first of all, and they need to be like big map play tests, tons of players, and that all gets piped into that dashboard. So we have that sort of bird's eye view of how everything's tracking. But then in those same playtests, we'll also have QA performing captures, just all over the place, so we'll also get those, and then they will get posted into a channel where we have like the CPU perf ringleader go through them and be like, what's that store? What's that store? And then just tag all the departments. And then it's like, oh my God, terrible store. And then everybody, kind of chips in, and they start, we all just start chatting in threads and figuring them out. We spawn tickets from those threads. And then what we did add, because I don't like to be reactive like this, I like to get ahead of it. We actually added a bunch of diagnostic code as well into the C++ that would detect a stall frame in Lua, and it would then report that information to us, and we then extended that so that we can even do it in live, and we can see when live players stall, and then we can collect those into buckets, and we can go, oh, this system's stalling in live, and we're not seeing that locally, and then we can actually update the Lua and fix that for the live game.
Do we do that with like lightweight JQ-prof spikes, or is this a separate system?
This is a separate system. This is the kind of Lua. It will capture a call stack earlier. If it has then determines that a spike has occurred, it'll take that buffer and it'll send it up.
Got it. So it's an actual Lua call stack rather than like a game,
yep.
like stack block or something.
Yeah, we should extend it.
Yeah, I know we do those on the server, right?
Yeah.
The rough spikes, but not on the client. So, and since Graham and some other people were talking SPU, JQ-prof is our old like SPU based profiler that lives on here. And so Mobin Fikri sort of follows up with a question, which is, beyond measurements profiling, did we develop like a best practices system, a specific code review process? I mean, obviously we have, the automation that's, like our designers on the UI team looking at that automation, or is it mostly engineering? Like, how do we feed back any of this stuff back up to the UI teams so that it's kind of an all-in effort rather than just the engineering team doing this post-mortem work?
Yeah, so we have, sorry, it's very late. Can you just repeat that question one more time?
What was our flow back? Like, so this is, a lot of this, as you said, this is a dedicated engineering performance effort, but,
oh, yes.
But how do we flow back best practices or
Yeah. Like this is kind of like a multi-pronged thing, like I was saying in the talk, like we can't, it's kind of futile to say like, hey, engineers, write code that's not slow, like that's kind of on a dev team of this size, oftentimes it's not like a single engineer who's like put, like a, nested for loop into a file, and it's going to be super, super slow. Normally, they're just making a small innocuous change, and then it's calling something and it's calling something, and the code is so complicated that that just happens to cause a performance issue. And then I would track them back, and be like, oh, it was this change that caused it, man. Like we never could have seen that coming, right? So I don't think that there's like designers or engineers doing anything wrong. It's just that the complexity of the system and potentially the way that it was originally designed and the fact that it hasn't been built to scale, these are the symptoms that we're seeing of those core problems. So that's why the efforts are really directed at diagnosis, and being able to catch regressions, and then having like bigger roadmap items to like, how do we actually fix this system for the long haul so that it does scale? And one of those, examples is creating the scripting language so that we actually move away from doing all of this iteration and writing all of this code, like that ends up turning into spaghetti, so that we can say, hey, we've got a system like Link, and you can just bind that to a grid, and we know that's going to be fast because we wrote that to be performant. So yeah, it's like a whole bunch of different things that we're doing.
Yeah, I mean, it's one of the fun things of, all the emergent complexity of this, right? It's almost never a straight line between, I know this change is going to have a performance impact and we're all aligned on that, right? It is almost always, oh, how do we end up in this situation? This was not what we were expecting. So, um, I've got a couple of questions on GC performance. I know this is more of a Jeff, question, but Sean Belay asked, "What do you mean by rubber banding the GC?" He wasn't clear what that meant specifically.
Yes, it's probably, I actually realized after I said that, I was thinking of like Mario Kart when you're at the end and you get like, brought forwards. But really what I was referring to was if you were starting to get closer to your, if there was a huge amount of memory pressure and you were reaching the emergency threshold, you could change that 100 microsecond that I defined to run for longer so that you could free more, so that you could say like, I don't want to get hit with a big emergency collection that's going to stall everything out, but because we've only got a meg left, I'm going to allow you to now run for 300 microseconds per frame instead of 100. And that sort of ramp is sort of what I was referring to.
Yeah, so basically it's a dynamic budgeting approach to some extent, or it's kind of
Yes.
reminds me of like the Schlemiel the painter effect too, right? Where like you can end up in these kind of like loops if you're not careful, where longer GC cycles are going to require longer GC cycles. Um, there's some in the weeds questions around ref counting. I'm going to skip those just because I don't think that's there was one question around like the overhead of the loopings and the call down to the GC. Did we ever like do any work to determine, whether it made more sense to kind of like hoist that time slicing like deeper down, or was it already set up in a pretty good way there? Like, was there like a non-amortized call overhead basically every time we looped down into the GC, I think is the question.
Yeah. So the like I wouldn't the like TLSF like allocator and its garbage collection pattern is like written by people way smarter than me. So I wouldn't be going down into that because it was developed for real-time applications. Using its minimally indivisible step where it's just saying, hey, GC, do the least amount of work you possibly can. I want to relinquish as little control as possible to you. When in that 100 microsecond example, it'll normally actually only loop there like 3 or 4 times because it can't really do anything in less than like 25 microseconds, depending on the platform. So yeah, the iterating like the iterative cost there is yeah, not significant.
Roger. We had some kind of general architectural questions too around like and I don't know if this is really in your bailiwick either, Simon, which is from Minhaju asked, curious about the UI rendering architecture. Are we doing like in draw calls per quads with alpha blending, like, or anything like that?
We are like we could certainly improve the rendering side of things. We are like, doing a lot of draw calls because we're like changing shaders, for different blend modes or for rendering fonts, so on and so forth. But that isn't where our bottleneck is, or at least the rendering guys haven't come and yelled at me yet. So I haven't had to go too deep down that pathway. It's all been very, very CPU bound, and that is like where we could do an enormous amount to actually change things. And I've got a lot of opinions on that as well. I think that menus and HUDs should be treated very differently. Menus can be hierarchical, but HUDs really got to be a lot flatter. And there was a question about C++, and moving things over to C++, how much does that help? And, that, really like Lua JIT is super fast, like it would help a little bit, but at the end of the day, it's the amount of work that we're doing the order and we're doing it, and the fact that we can't parallelize it, that's really what's costing us.
Yeah. Yeah, related to that was from Elizabeth Baumel, that question, by the way, and Sean asks a sort of related follow-up, which is, I mean, I think he's asking very philosophically, why do we write in script-based UI? That's a big question. I don't know if we can, very briefly kind of talk about the Louis ecosystem and kind of what it allows us to do there. If you have a particular point of view beyond, GC bad.
Yeah, look, I mean, at the end of the day, it's really about being able to drive the UI, with data and making it accessible for designers and for programmers to make changes without like needing C++ programmers to be involved. And so there's a lot of value in it, having a high level scripting language, and I think it can be employed in a much more responsible way. And I think that there needs to be a balance, and so I do tend to sort of err on the side of, C++ for the HUD is, oftentimes, much more performant and better. But when it comes to all of the menus and the complexity there, like, we can have a different system and we can use a scripting language and we can be higher level and we can afford the GC, for example, in the menus. We just can't really afford them at runtime in the game.
Yeah, there's a corollary here, which is, ask us about our WebKit renderer and when it's permitted to be used as well. We're at time, so thank you again so much, Simon, for this wonderful talk, for being up so late. Best of luck with your impending excitement, and we will take a 15-minute break, 14-minute break now, and be back at 10:45 for our final and last talk from Steve McCauley and Matt Patinio on the sort of presentation on Sony Mnemonic Studios Maya as a tool for building games. Thanks, everyone.